So now the trends in electronegativity, okay, and what is electronegativity? Okay, electronegativity is a measure of the attraction one atom has for another. Okay, it's a measure of the attraction one atom has for another atom's electrons in a bond. Okay, normally a covalent bond. Okay, it's a measure of the attraction one atom has for another atom's electrons in the bond. Okay, so it was first described by Linus Pauling. Okay, I will expand on him in a different video. So so as you move, so that's the definition of it. Okay, what are its patterns? Over the period. What are its patterns? Okay, how does it change over the periodic table? Okay, hope you can. What are its patterns? How does it change over the periodic table? So, as you move, going from left hand side to right hand side. Okay. Electronegativity, it increases, okay? And going from top to bottom, okay? From lithium down to cesium, francium, the electronegativity decreases. Okay? So these are the main moving from left hand side to right hand side, it increases. Going from top to bottom, it decreases. Okay, that's the main key facts. My earlier video on covalent radii, I should have drawn it like that, but it doesn't matter too much. So yeah, left hand side, going from left to right, it increases. Going from top to bottom, it decreases. Okay? So that means that fluorine equals most electronegative element. And cesium, francium in fact, and in high grade you tend to go with cesium, equals least electronegative element. Okay, I mentioned cesium because it's used more in questions and problems, where the francium is actually the least electronegative element. So why does electronegativity increase as you go from left to right and decrease as you go from top to bottom? Why the patterns? Okay, it increases because number of protons, because the number of protons is increasing as you move across the row, okay, the period. An electronegativity, it decreases, okay, due to the number of shells, that's electron shells, increasing. So as you get more and more protons going across the period, the row, from left to right, the nuclear charge gets more and more positive, and so it pulls more and more strongly on other atoms' electrons. So fluorine, as you can see, is 9 electrons, okay? It pulls much more strongly than lithium, it's 3. That's the strongest. And it pulls much more, yeah, it pulls more strongly than lithium. Chlorine pulls more strongly than sodium. Bromine pulls more strongly than potassium because there's more protons. It has a much more positive nucleus, so it pulls more strongly than the other atoms' electrons. Whereas when you go down, although the nucleus is getting bigger, there's more and more shells of electrons. So the nucleus has very little effect. The nuclei of cesium, francium, so they take the extreme end, they have very little effect on another atom's electrons because the nucleus is there's a lot of shielding around it, okay? There's yeah, so with francium there's sort of multiple shells around it, like that, okay? That's why when you have a positive nucleus, it has very little effect on another atom because there's too much shielding, okay? So this is measured. You need to learn to use your periodic table, okay? Data periodic table, okay, for high grade. Turn to the bit of electronegativity scales, okay? So you got Electronegativity Scale. It's called the Pauling scale. It actually mentions the name Pauling scale here. As I said, Linus Pauling created it. American biochemist. So if you take for fluorine, that's the most electronegative element. Okay, fluorine. That's electronegativity of 4. Whereas cesium, somewhere, hard to find when you want things and you can't see them. Bromine, rubidium. It's a value of 0.8. I don't know where it is. Cesium. Where is cesium? Cesium, okay? So that's value of 0.8, okay? Sometimes elements do share the same value. You might get a value of 2 here for boron. Another one might have a value of, what else? Sorry, there's 1.9 each, okay? Nickel and copper are values of 1.9. Sometimes atoms do share the electronegativity value, the same value. But if if 2 atoms are joined by a bond, and one atom has a higher value than the other one, then you'll get it. Well, it causes that form of polar covalent bonds, but it means you'll get the stronger atom will pull the electrons off the weaker atom. Okay, so yeah, putting that aside, a couple more things to explain. So when you have hydrogen chloride, okay, maybe I'll draw it here. Okay, because this is much more electronegative than that. Hydrogen, for the record, is electronegativity value of 2.2, and chlorine is electronegativity value of, if I can find it, chlorine of 3, okay, yeah? So that's hydrogen is 2.2, chlorine is 3, okay? Fluorine is 4. So when you draw to illustrate how this behaves, you draw the atom sort of like that. Could be drawn better actually. So you sort of draw it. So basically you've got a lot of negative charge over here and very little positive charge there, okay? So it becomes very distorted. If I can try to draw it better, it would help you. That's better, okay? A bit better. So you got a lot of negative, positive, okay? So all the electrons are being pulled towards the fluorine atom, okay? Or being pulled towards the chlorine atom, okay? So you draw them as this asymmetrical shape, okay? Which is polarized. This is actually called a polar covalent. I'm not spelling it very well, am I? Polar covalent bond, okay? Polar covalent bond because it's polarized, okay? Whereas a normal covalent bond like that, the whole thing, as I said in early videos, that's symmetrical. Okay, that's symmetrical, it's not polarized. This is asymmetrical, it's polarized, okay? So that's the effect of a strongly electronegative atom bonding to a weakly electronegative atom, okay? Yeah, so yeah. I hope that's clear. Bye. If you have any questions, please ask. If you would like me to clarify anything, please ask. Okay, please say. And please support my channel, subscribe, press bell, and like. Thanks very much.